If you're designing cryogenic systems, you don't need to become a chemist. But there are several physical properties of liquid nitrogen that every engineer should understand, because these properties determine why cryogenic systems are designed the way they are. This isn't a chemistry lesson. This is engineering. Take a look at liquid nitrogen. At first glance, it looks almost identical to water. It's clear, colorless, and flows like a normal liquid. But don't let its appearance fool you. This is one of the most extreme fluids used in industrial engineering. Its density is approximately 808 kilograms per cubic meter, making it about 20% lighter than water. However, density isn't what makes liquid nitrogen special. Temperature is. Liquid nitrogen boils at minus 195.8 degrees Celsius under atmospheric pressure. To put that into perspective, if your workshop is at 20 degrees Celsius, then every object around you is effectively a giant heater. Everything surrounding the liquid nitrogen is trying to warm it up. That's why liquid nitrogen is always boiling, even when it's simply sitting in an open container. This is probably the single most important number to remember. When liquid nitrogen evaporates, 1 liter of liquid becomes approximately 700 liters of nitrogen gas. Imagine a 1-liter milk carton suddenly expanding into enough gas to fill several household refrigerators. That's why nitrogen is transported and stored as a liquid. It's compact, efficient, and economical. Only when it's needed is it converted back into gas. Many people think liquid nitrogen is some kind of special chemical. It isn't. Nitrogen already makes up 78% of Earth's atmosphere. Industrial plants simply compress air, remove impurities, cool it to cryogenic temperatures, and separate nitrogen from the other gases. It's not created through a chemical reaction. It's simply purified air that's been cooled until nitrogen becomes a liquid. Liquid nitrogen flows extremely easily, even more easily than water. Because of its low viscosity, it can find its way through very small leaks and imperfections. That's one reason why cryogenic piping systems require extremely high manufacturing quality and tightly control. This is where material science becomes critical. Structural carbon steel performs perfectly well at room temperature, at minus 196 degrees Celsius. However, it can lose its ductility and behave almost like glass. For this reason, cryogenic equipment is typically manufactured from materials such as austenitic stainless steel 304L 316L, aluminum alloys, copper alloys. The material isn't chosen for corrosion resistance alone. It's chosen because it remains tough at cryogenic temperatures. Everything shrinks when it gets cold. Stainless steel contracts approximately 3 millimeters per meter when cooled from room temperature to liquid nitrogen temperature. That means a 100-meter pipeline can become nearly 30 centimeters shorter. This is why cryogenic pipelines require expansion loops, sliding supports, or expansion joints. Otherwise, the pipeline will simply pull against equipment and supports until something fails. Standard rubber seals don't survive cryogenic service. They become hard, brittle, and lose their sealing capability. Cryogenic systems therefore use specialized sealing materials such as Teflon, spiral wound metallic gaskets with graphite or PTFE filler. Choosing the right gasket is just as important as choosing the right pipe material. No cryogenic tank is perfectly insulated. No matter how good the insulation is, some heat will always enter the system. As a result, a small amount of liquid nitrogen continuously evaporates. This is known as boil-off gas, BOG. Every cryogenic storage system must be designed to safely handle this continuous gas generation. If we cut a cryogenic storage tank in half, we'd find 2 vessels, an inner vessel, an outer vessel. Between them is a high vacuum, often combined with multi-layer insulation. Think of it as a giant industrial thermos flask. The purpose is simple: keep heat out. The less heat enters the tank, the less nitrogen boils away. The most dangerous liquid nitrogen isn't flowing. It's trapped. Imagine two closed valves with liquid nitrogen trapped between them. As the liquid warms up, it expands. Pressure rises dramatically. Without pressure relief, the pressure can become enormous. That's why cryogenic piping often includes thermal relief valves wherever liquid can become trapped. Nitrogen has no smell, no color, no taste. If enough nitrogen escapes inside a confined space, it simply pushes oxygen out. People don't notice anything unusual. They simply lose consciousness because there isn't enough oxygen to breathe. That's why oxygen monitoring systems and emergency ventilation are essential in cryogenic facilities. Liquid nitrogen freezes living tissue almost instantly. You may have seen demonstrations of the light and frost effect, where a tiny droplet briefly floats on a layer of vapor. While fascinating, this should never be considered safe. Working with cryogenic liquids always requires proper PPE, face shield, safety goggles, cryogenic gloves, protective clothing. You can't simply open a valve and flood a warm system with liquid nitrogen. The system must first be cooled gradually. Think about pouring boiling water into a frozen glass, or ice water into a very hot glass. Thermal shock can crack materials. The same principle applies to cryogenic equipment, only on a much larger engineering scale. Seeing thick ice on a cryogenic vaporizer or an uninsulated fitting often looks alarming. In reality, it's usually completely normal. Moisture from the surrounding air freezes on the cold surface. That's actually a sign that the equipment is doing its job. However, engineers must also consider where that ice and the water produced during defrosting will eventually drain. Now we understand why cryogenic systems look so different from ordinary water or steam systems. Extreme temperatures, thermal contraction, boil-off gas, specialized materials, vacuum insulation, and pressure relief systems all exist because of the unique physical properties of liquid nitrogen. In the next video, we'll take everything we've learned today and apply it to a real cryogenic storage tank process diagram. We'll break down every line, every valve, and every connection to understand how a real cryogenic storage system works before we start building it in AutoCAD Plant 3D.